Well, hello again there. Welcome to today's JAMB class presented to you courtesy of O3 Schools JAMB app, the only app you require preparing for your JAMB. The app has a wide range of features designed to ensure you get the best possible score that you can get in your examination. Now, all you have to do, simply download your app on either your Android phones or your Windows laptop, install this application, and if you install it, you notice first of all that your options, what you can do with this app is limited. But then you have to activate this app. Activation costs 2,500 naira only, no more. And once you activate this app, you shall get access to all the features as provided in this app. There is information there, advice on how to choose your schools. This of courses offered by the schools, the subjects you require for those courses. You also have obviously your past questions. You can do it in mock exam mode. There's even a feature to search for questions per topic in each subject, such that as you read or as you learn anything, you simply have to search for that particular question on your O3 Schools JAMB app and then answer the questions in that topic. Once you can answer all, you know you are ready. If you can't, no further reading might be necessary. You see, the app has many useful features which will benefit you. And the activation is very, very simple. Simply follow the steps as you can see on the app. There's no reason to fear, like some people would say, that what if they pay and their money doesn't, get used and they get scammed. I'm assuring you here that no, this app is not like that. If you've had negative experience, yeah, you shall have a positive experience. O3 Schools Jam app is the way. And with that, let's just start this class. We shall be looking at waves. And in this class, we'll just be studying properties and types of waves. Okay, now first of all, what is a wave? A wave is a disturbance which travels through a medium, propagating energy without causing a permanent displacement of the particles of that medium. Now, this might sound like grammar. What is a wave? Simply, in the simplest manner, you simply have a disturbance, a shake, if you will, that then moves through a medium, and as it moves, it is transferring energy. But what makes it special is that once it transfers this energy through the medium, it doesn't cause any permanent displacement of the particles of that medium. If I use a piece of wood to hit someone, for example, I'm actually transferring energy. Yes, kinetic energy from my hand is hitting him and he may fall. That's motion, he moved. I transfer the kinetic energy from the stick to him. However, my stick was no longer where it was to transfer the energy, it has moved. But in a wave, for example, imagine you take a rope and then you create ripples in this rope by shaking the rope. If I have something here, that thing is going to fly, it's going to fall off. How? Because energy was transferred from this point down there. But did my rope itself truly go anywhere? No. My energy simply traveled through the rope until it came here and moved this. The energy was transferred without any permanent displacement of the molecules which make up this rope. See, and that is basically what a wave is. Now, to study wave, obviously, the first thing you must ask yourself is types of waves. But then, before you can analyze types, you must ask yourself, okay, types based on what? And in this case, an example is human beings. If I ask you types of human beings, you'd have to ask me, based on what? Based on religion now, you can have your Christians, your Muslims, your traditional worshippers. Based on color, in Nigeria, I like to say we have fair and chocolate or black. Those are colors. Based on race, we have the Igbo, the Hausa, the Yoruba, and all the other tribes. Based on gender, male and female. And therefore, you see, before you can talk about type, you must ask yourself, on what criteria am I basing these types? And in this case, we also have that. Now, based on type, can I have one based on medium of propagation? That's the first classification. Then two, we can also have based on direction of propagation. And thirdly, we can also have based on distance being traveled. So Those are the three criteria we look at when analyzing the types of waves. Now, looking at the first type, based on medium of propagation, over here we have what is known as mechanical and the electromagnetic waves. Now, what are the differences? A mechanical wave requires material medium. A mechanical wave cannot travel even if there is nothing for it to travel on. While electromagnetic waves do not require any material medium whatsoever. They are able to move without any object, without a road to travel on, in the manner of speaking. So, mechanical waves, there are many examples. We have sound wave, we have water wave, and we also have wave on a string. Cannot have a wave on a string if there is no string. Cannot have water wave, obviously there is no water. While for your sound wave, you may not have noticed this because there's always air around us, but sound actually travels through the air, or through solid, or through liquid. It must travel through something. If there was no air, then there shall be no sound. Therefore, in space, there is no sound. Unlike some of the movies we watch where you can see things exploding in space and you can hear sounds. In natural space, there is no sound. Everything is quiet because there is no particle or no material for this sound to travel through. While electromagnetic waves are quite many, there is radio wave, infrared wave, ultraviolet, your light wave. There's also X-ray and there's gamma rays. So electromagnetic waves, these ones do not require material medium whatsoever. For example, the light from the sun coming to Earth passes through space where there's nothing. Doesn't require material medium. Those are the difference. Then, based on direction of travel, we now have the two types, which are longitudinal waves, and your transverse waves. Okay, again, we look at the differences. Now, a longitudinal wave travels parallel to the distortion which is causing it. For example, sound wave. If you have a speaker and your speaker is making sound, you hear the sound. Basically, you put your ear, this is your speaker, you put your ear here, you hear the sound clearest in front of it than above it or below it, because the wave is simply traveling parallel to the disturbance beside the speaker which is causing it. But transverse waves, on the other hand, travel in a direction perpendicular to the disturbance which caused them. A good example which you cannot picture is your water wave. If I have water here, if I drop a stone into this water, and the stone goes straight down, ripples are created in the water. And where do they go? Outwards, like this. Therefore, the direction causing this was going down, while the waves were going perpendicular to it. So that's the difference. Longitudinal waves travel parallel to the disturbance, transverse travel perpendicular to this disturbance. Example of longitudinal wave is sound wave. One good example of your transverse waves is water wave and simply all electromagnetic waves. So that's one thing to note. All electromagnetic waves are transverse, but not all transverse waves are electromagnetic. It means everything electromagnetic falls under this group, but it's not the same that everything under this group can also fall under electromagnetic. Well, last but not least, based on distance traveled, we have stationary, or according to some places, standing waves, and we also have progressive wave or traveling wave. Now, what is the difference? A stationary wave simply doesn't really move anywhere. A wave on the string is a good example. Once it gets to the end of the string, your wave terminates. It can't pass there. It has a boundary. A progressive wave, on the other hand, doesn't really have a boundary. It can only stop when the energy powering it has been exhausted. Therefore, if I was to shout, the wave doesn't terminate once it comes out of my mouth. No, it keeps on going, but the wave decays until it gets to a place where you can no longer hear that sound. So that's the difference. Stationary waves, they have a boundary. They cannot exit. They cannot pass there, like your progressive, like your wave on a string, rather. while progressive waves can actually travel. Now, those are our types of waves based on the following criteria. The next two we shall then look at are then properties of waves. We've talked about types. What about properties? How do I know that any material I'm looking at is actually a wave? Now, we have about 5 properties of waves that we'll look at. 5 properties. Number one is reflection. Number two is refraction. Number three is diffraction. Number four is interference. While number five is polarization. So, to identify that something is a wave, it must possess at least 4 of these properties. And why do I say 4 and not 5? That's because this last one here, polarization, only works for transverse waves. That's the difference. Every single wave can undergo these 4, but only transverse waves can undergo polarization. What is polarization? It's simply, if you have a normal wave, it moves like this. Polarization is a process by which we make sure that this wave's vibration exists in only one plane. Therefore, it's like we are cleaning the bottom and the wave can now only exist above. This is polarization, and it can only work for your transverse waves. That's that. So now, let's go and start from the top after explaining polarization. We have reflection. What is reflection? Reflection is the bouncing back of a wave when it hits an obstacle. So the wave goes forward, hits an obstacle it cannot pass through, and bounces back. We'll treat expansion, or rather, we'll treat reflection of waves in a different video, which you can check at the channel. You see the video there. We treated reflection as a topic on its own. So there's no need for too much explanation over here. Just know that it's the bouncing back of waves, e.g., with a mirror. Your light hits the mirror and bounces back. That's reflection. Then there's refraction. Refraction is simply the bending of the wave as it crosses the boundary between two media of different densities. Reflection was for when it cannot pass through. What if it can pass through? When it passes through, instead of passing through and coming out the way it entered, there's usually a change in the wave, a change in the velocity, wavelength, and the direction. This is what we refer to as refraction. And just like reflection, we also treated refraction as a topic on its own in a separate video. So I don't have to go too far into it. We did refractive index and a lot of other things. So please again, check the channel and you can see the video for refraction. Now, diffraction, we didn't treat diffraction in a separate video. What is diffraction? Diffraction is the spreading of a wave as it passes a tiny boundary. Say, for example, if you ever played music and you open your door just a little bit, the sound you hear outside doesn't seem commiserate with the size to which you opened your door. You'd expect to hear just a little sound. But the thing is that as you have a small boundary and your wave is passing through, when it comes out, it begins to actually spread out as it comes through this hole. And the bigger the wavelength, the more the diffraction effect. So a wave with a big wavelength can diffract more than a wave with a smaller wavelength. And for that reason, sound, which has a big wavelength, experiences a greater diffraction than light, which has a much smaller wavelength. So the wavelength of sound is greater than the diffraction of sound is greater than the diffraction of light, because the wavelength of sound is bigger than the wavelength of light. Okay, and then we also have interference. What's interference? Interference is in the particle sense. We try to observe interference. Interference is like a collision between two waves. When two waves meet each other, what happens? However, please note that for interference, the waves must have the same frequency and the same amplitude before they can interfere. So two similar waves of the same frequency and amplitude, when they meet each other, interference occurs. And we have constructive interference, and we also have destructive interference. Now, obviously, destructive means we are destroying, we are breaking down. In destructive interference is what happens when two waves meet each other and then they reduce. While constructive interference is when they meet each other and they increase. Now, however, what determines whether a wave should be constructive or destructive is the phase angle, which we shall look at shortly. But just note that if two waves are perfectly in phase, then we get totally constructive interference. If this was one wave and the other wave was also moving perfectly in the same manner, when they meet, they will form a wave times two of the initial size. While a destructive wave occurs when they are perfectly out of phase. That is, as this one is going up, the other wave is going to be coming down. If they meet here, they're going to completely cancel out. And in that case, you now get a totally destructive interference. While on the other hand, if they are partially out of phase, then they end up going somewhere which is partially constructive and also partially destructive. So those are the properties of waves. However, knowing the properties now, when we want to analyze waves, what are the different things you must know when talking about waves? There are several concepts that one must know when thinking or talking about waves. For example, we must know what is wave speed. We must know what is wave speed. There is speed or velocity of the wave. There is frequency. There is period. There is wavelength. There is amplitude. There is phase. We must know these six steps. Let's start off by drawing the simplest representation of a wave. If this is the wave, this is your y-axis. This is both the x and time axis. There's an angle here, theta. Then this maximum distance. So let's start off by simply with amplitude. What is amplitude? Amplitude is the maximum displacement of the wave from the equilibrium position. This straight line is the equilibrium position. So the highest point it can go is what we refer to as amplitude. So maximum displacement. And you should note that this displacement equals this displacement equals this displacement. So that is amplitude of the wave, represented by A. Then we also have wavelength. What is wavelength? This guy, and the symbol is lambda. Lambda. What is wavelength? Wavelength is the distance from one crest to the next successive crest. Sounds like big grammar, I know. But basically, we mean if this is a crest, these top points are crests, the bottom points are called troughs. So the distance from this crest to this crest is one wavelength. Here to here, also one wavelength. In fact, I can also pick a point here from here to the corresponding point exactly like that. It's also going to be a wavelength. That's wavelength. What about period? Period is the time taken to complete one cycle. And I think we should also explore the cycle is. A cycle simply refers to one complete revolution, one complete movement of the wave. So from here up, down to start going up again is a cycle. So a period is the time taken to complete one cycle. I have the formula. Period big T equals to the time taken to complete as many cycles as you want, but the number of cycles completed. So time per cycle, that's period, and the unit is seconds. However, frequency is now the number of cycles completed per second. Period was time per cycle. Frequency F is cycle per time. And the unit of frequency is hertz. Hz is the short form. It should have been per second, but it is preferred to call hertz after Frank Hertz. Then we also have velocity of the wave. Velocity of the wave simply measures how fast, obviously, the wave is moving. And the formula for velocity of the wave, v equals to f lambda. That's the formula for velocity of the wave. Then the one also thing you should notice, if you look here, f and t, they're almost the same, right? Just that they are reversed. Therefore, we should know that f equals to 1 over t. And that is the next thing we should know for a wave. Well, last but not least, we also have phase there. What is phase? Now, two waves are said to be in phase when they reach their peak and their minimum destinations at the same time. That means as one is going up, the other one is going up. If they reach the topmost point at the same time, and also come down and meet the downward point at the same time, then they are in phase. Something like this. They might not have the same shape, but they are meeting at peak at the same time, but some at the same time, equilibrium at the same time. And that is what it means to be in phase. If it's not like that, then they are said to be out of phase. So these are the terms we shall use in analyzing wave. And now, this is the simplest diagram for a wave. But to analyze this, if you remember, this looks like a sine graph in mathematics. This can be referred to as a sinusoidal waveform. And because it is a sinusoidal waveform, I must know that y equals to a sine theta. That's the first thing I know. However, what if this wave is a bit out of phase? Then I must introduce a phase angle, a sine theta minus phi. Now, please note, in some textbooks, they use theta plus phi. As we are concerned, it doesn't really matter. Plus, minus, they are irrelevant for the type of solving we are currently doing. Like, this is where it's important, but not here. So, this is my basic formula for the wave. Then, if I look at my theta, I should remember from your simple harmonic motion that angular velocity omega equals to theta over time, and therefore theta equals to omega t. While my phase angle phi equals kx. Therefore, y equals to a sine, instead of theta, I shall be having omega t minus kx. Okay, then again, recall from angular velocity in superharmonic motion, y equals to a sine 2 pi f, which is omega t. While your k constant here is actually given by 2 pi over lambda. Here is x. So this is one basic formula for a wave, which you should note. But then, if you also recall, f as we have here is 1 over t. So y could also be equals to a sine 2 pi t over t time over period minus 2 pi x over lambda. Yet another representation of a wave. But we don't have to stop there. Ask ourselves, is there any other way they could represent it? And yes, there is. What they could then do is, you could say y equals to a sine, and then they'll factorize out 2 pi over lambda. This make x stand alone. That will give a sine 2 pi over lambda comes out into, if 2 pi over lambda is the quantity of this place, does not have lambda down, then lambda has to appear up to cancel it out. So I'll now be having lambda t over period minus 2 pi over lambda leaves there, I have x. Now you may be asking, what can I do with this? Simply remember here, if v equals to f lambda, then v must be equals to turning f to 1 over t, that is lambda over t. Implying that where I see lambda over t, I can put v. So y equals to a sine 2 pi over lambda into vt minus x. I know some of us might be panicking right now looking at this and saying, how am I supposed to memorize all this? The good news is that you don't have to prove this. You're writing JAMB. I'm not going to be proving in JAMB. You just have to know 1, 2, and 3. And how do the questions come? They'll give you an expression. All you simply have to do is ask yourself, what does that expression resemble the most? Any one expression, if I give you an expression that has 2 pi over lambda outside, that has any number outside between your sign and your bracket, know you are dealing with this type. Why, if there's no number outside, you can be dealing with this or this. But keep in mind that they are basically the same thing. And once you know this, you are now ready to open your O3 Schools JAMB app and begin to solve questions on that waves. So let's see. Our first question comes from the year 2009, question 26. And yes, you can see the question on your screen, also on your O3 Schools JAMB app, so I will not have to draw it. In this question, I've been told there's a slit, a wave passes through, and emerges. What phenomenon is demonstrated in diagram above? Now, if you remember what we just learned under the properties of waves, there's reflection. Reflection is bouncing back, not passing through. So that's not it. There is no deflection under properties of waves, so we're ignoring that. I will jump to option D first for now. There's refraction, which is a bending as it pass through the boundary. That's what's happening here. Here, there's a space and the waves are passing through. And the only property that gives you such a phenomenon is obviously diffraction. So that is option C. You see, the questions are very, very simple. But now we have one to solve. So let's go with our solving. If a light wave, these are questions to solve. If a light wave has a wavelength of 500, now so we'll also call this Nm. Keep in mind, please, that N here represents nano. This is 500 nanometers. And what is nano? Nano is simply a prefix which stands for times 10 raised to the power minus 9. So that's my wavelength. I'm being asked to find the frequency of the wave, given that speed of light equals to 3 times 10 raised to the power 8. Now that's an electromagnetic wave and the speed is quite fixed. That's why it is referred to as c here. So as c is the velocity, which is the same thing as v, we know that c equals to f lambda. And if I want to find f, f must be c over lambda. What's my c? 3 times 10 to the power 8. And what's my lambda? 500 times 10 to the power minus 9. So what can I do? First things first, let's see if putting this in standard form will help me out. This will give me 3 times 10 to the power 8 all over. I'm moving my point backwards twice, which is I'm adding 2 here. 5 times 10 to the power minus 7. So number divided by number. 3 over 5 is 0.6. Then 10 raised to the power 8. Division is minus 7. 0.6 times 10 raised to the power 8 minus times minus is plus. So 7 is 15. Then I'm going to move my point forward once and add 1. So sorry, if I move your point forward, you are subtracting 1, not adding. So that will be 6 times 10 raised to the power 14. Frequency is measured in hertz. So my answer is obviously option B. See, this question was from the year 2009, question number 30. Now for the next question, we're going to the year 2010, and now we are actually looking at question 24. The wavelength of a wave traveling with a velocity of 420 meters per second is 42 meters. The wavelength is 42 meters. We have to find the period. Did we have a formula relating velocity, wavelength, and period? Yes. We noted that V must be lambda over period because period is 1 over frequency and frequency is 1 over period. Therefore, to find my period, cross multiply lambda equals to T equals to V over lambda. My T will be V for 20 over lambda 42. That is simply 10 seconds. So you see, another very, very, very simple one. Um, Funny enough, though, we do not have 10 seconds in our options, but we're going to stick with that as our answer. What can you do? If you have a question like this and you're not quite sure what is wrong, and you want to try and imagine a possible alternative in your JAMB, what could you do? You could assume, for example, that maybe this should have been in centimeters. If we try that, will that work? No, because we convert this from centimeters to meters, that will make lambda reduce. I'll make my answer increase. But if you look at the options, all my answers are smaller. Therefore, I cannot try centimeters. I could then say, okay, what if this instead was the one that was in centimeters per seconds? This was centimeters per seconds. To convert to meters per seconds, I would have to divide by 100, which will make it 4.2 meters per second. So that instead of 420 here, I'll be having 4.2. And if I do 4.2 over 20, I then get 0.1 seconds, which is in my options, and that is option B. Now, please note, I don't recommend you wasting much time trying to correct a question in your exam. If you solve and you know you solved correctly, but your answer does not appear in the options, I will advise you to simply guess the closest one and move on. Or if you want to, you could leave that question and come back and tackle it if you know you can finish your exam on time. But do not waste your time when you know you solved the correct thing already, trying to resolve and resolve to get their answer. As long as you are sure that your first solving was correct. Okay? Our next question is from the year 2011, and this is question number 21. Which of the following types of waves needs a medium for propagation? Remember, the type that needs medium are mechanical waves, while electromagnetic waves do not require medium. So option A, X-ray, obviously electromagnetic, so no. Sound wave is mechanical, so that is my answer. Mechanical waves are the ones that require material medium. Then the next question, 2007, question 8, also theoretical. The phenomenon of light bending around an obstacle is known as diffraction. See, that's light bending around the obstacle, which is the spreading out after passing through a tiny space. Diffraction, option D. Next, we have a diagram. This one is quite interesting. This is from the year 2006, question 34. Now, there's a diagram which you can see obviously on your O3 Schools app. Then in this diagram, I have a wave, right? Now this wave moves, and the last time we noticed on the time part, the horizontal part of a graph, is that the time it used was 4 seconds. However, in that 4 seconds, how many cycles has it completed? You noticed it went simply like this. This is one cycle, go and come. Therefore, number of cycles is 1. And what is your wavelength? Wavelength is the distance from peak to peak, crest to crest, or trough to trough. Also, we could say wavelength is the distance from middle to middle. But do I need the wavelength right now? No. The reason why I'm simply asked for frequency. I don't talk about wavelength. I just need to know that for frequency, frequency is number of cycles over time. How many cycles? 1. How long? 4 seconds. And 1 over 4 must give you 0.25 hertz. See, my answer is option D. So as long as you know your basic steps, you should not be having any issue. Okay. Question 4. For question 4 again, this is theoretical. Let's look at the answer. This is from the year 2004, question number 40. 2004, number 40. Then we are told 1 is wavelength, 2 is method of propagation, 3 is wave velocity, 4 is frequency, and 5 is energy. Which of the above is used for characterizing wave? Which of the following are terms used when describing waves? Do we use wavelength? Yes, of course. So we know our option must have 1. Do we use medium of propagation? when describing a wave? No, that's under types. Well, don't use it when describing the wave. Do we use the wave velocity? Of course. So 1 and 3. Right now, I don't have to continue analyzing. But look at my options. Only option D contains 1 and 3. Therefore, I know my answer must be D, which is 1, 3, and 4. Because remember, when describing wave, you must look at, like the terms we described, you must look at the velocity, the frequency, and the wavelength. So those are our terms we use for describing wave: 1, 3, and 4. Okay, next up, we are in the year 2004. Now, question number 37. Again, you can see the diagram. The phase difference between waves P and Q is what? Now, if you look at this diagram, it's something like this. I'm going to draw a simple version here. Wave Q is like this, while wave P is more like this. So if you notice, wave Q is at its bottom, while wave P is still behind. Now, this one's peak is where this one's bottom is. Therefore, it must mean that it is basically a quarter of a cycle behind. And a cycle is 360 degrees or 2 pi. So what's a quarter of that? 2 pi over 4, which is pi over 2. See, answer is A. This is more mathematical than physics. This is why you need to have a good handle of your mathematics. Just because I know this wave is having a peak here, right? This one is here. Therefore, by the time this one has reached here, this one has already gone far again. So there's a gap between them. Therefore, that gap is pi over 2 radian. Or if it was in degrees, it was maybe 90 degrees. So that's that. Okay. Next. Again, theoretical. From the year 2002, question 18. The property that is propagated in a traveling wave. Property being propagated in a wave is what? Frequency, amplitude, energy, and wavelength. Now, if you recall, even from the definition, we said a wave was a disturbance which travels through a medium propagating energy. We are actually moving energy. Therefore, the property being propagated obviously must be the energy, and that is option C. So, okay, we now have a question. This one will require a bit of solving. A traveling wave moving from left to right has an amplitude of 0.15 meters, a frequency of 550 hertz, and a wavelength of 0.01 meter. The equation describing the wave is what? Now, obviously, we know the general format is that y equals to a sine blah blah blah. But if I look at these my options, in all of them, I'm having a number after my sign. Notice option A is sine 200 pi, option B is sine pi, C is sine 5.5 pi, and D is also sine pi. Which implies if a number is coming out, like we said before, therefore that must mean there's only one type of formula that has a number outside. If you remember, that will be A sine 2 pi over lambda into Vt minus x. That means for my wave to be described in one of the options, that must be it. What can I do? It means that to get everything I need, I must know V. And that's basically I need to know. I know A is given to me directly. I know lambda also given to me directly. But can I get V? Yes. V equals to F lambda. That will be 550 times 0.01. And 550 times 0.01 is 5.5. And therefore, quite simply, y will be equals to the amplitude A 0.15 sine 2 pi over what is lambda? Lambda is 0.01 into V 5.5 C minus X. So that will be 0.15 sine 2 over 0.01 is 200 pi into 5.5t minus x. And that is option A. If you look at option A, there's a small difference. Option A is actually 0.15 sine 200 pi into x minus 5.5t. Now, if you recall, I told you the big difference we care about, we don't actually mind, even if x coming first or the t own coming first, even if it's plus, we're simply focusing on the numbers inside. So, this is my answer. Is that okay? The steps are very simple. Okay. The next question we actually have now is asking us a very simple thing. It says, which of the following conditions are necessary to produce interference fringes? For two waves to interfere, for interference to occur, what must be there in the wave? Option A, or rather, we have numbers now. The first one is coherence. Next one is same frequency, same wavelength, and same intensity. Now, if you remember when we explained what is meant for interference, we didn't measure intensity at all, so that's out of it. Now, you may also say we did not measure coherence, but we said the waves must be moving similarly to each other for interference to occur, same direction. That's what coherence means. They have the same form, same frequency, yes, and they have the same wavelength. Therefore, any wave with those properties can undergo interference. That's that. This is from 2000, question 13. Now, from the year 1997, question 47, there's a diagram. The question is asking us basically, they are going to interfere, but what kind of interference will occur? Now, if you look at these two waves, they both go up together and come down together. They are in phase. And because they are perfectly in phase, what we undergo is constructive interference. They're going to join together to form a bigger wave. Therefore, my answer must be option C. It is constructive. But C and D, D is saying they will construct to form a wave of smaller amplitude, while C is saying they construct to form a wave of larger amplitude. I cannot join two things together and they are both positive and get a smaller thing. So when they go constructively, I get a wave of larger amplitude. See? So that's that, option C. And then last but not least, from the year 1997, question number 23. Ripples on water and light waves are similar because both what? What is the similarity between ripples on water and light wave? What do they have in common? A says they have the same frequency. Absolutely not. Light has a very high frequency. B can be refracted and diffracted. They are both waves, right? Yes. Because they are both waves, they both share the properties of refraction and diffraction. So that is my answer, obviously. But just look at the other options. C says they are longitudinal waves. While as we are aware, they are not. They are transverse waves. They move perpendicular to the vibration causing their motion. Why this says they have the same velocity? Absolutely not. Light has a speed of 3 times 10 to the power 8 meters per second. Pretty much the fastest thing in the known universe. While a water wave has a much slower, very much slower velocity. So my answer is obviously option B. And with that, I'd like to tell you thank you very much for watching this video explaining waves and its properties. Remember to subscribe to this channel to get more videos teaching you various topics across various subjects. Also remember to get your O3 Skills JAMB app and activate it to enjoy its full functionality. My name is Athanasius. Thank you very much for watching.